Let me few announcements. The due date for the next assignment, number 7, I have extended it for another week because we have exam next week. So it will be due after the exam, the Tuesday after the exam. So you have roughly 2 weeks. You can manage the time. If you want to do it before, that's fine. If you want to do it afterwards, that's fine as well. And I expect probably we'll have 2 more assignments after that in this course. So total of 9 assignments and then maybe 1 more quiz. So today we will have a quiz and 1 more quiz. Now this quiz would be kind of preview for your next midterm exam. I did check because some people expressed concern that the weight on the final exam is quite high, 40% and 20 on the midterm. I checked with the person who taught it last time and he had 2 midterms and 1 final. All of them together were about 95%, okay? And quizzes were 5%. So I'm not far off. I have 80% for all the exams, 3 exams, 20% for assignments and quizzes. So that each quiz will be treated as equivalent to an assignment. Okay? What else do they want to? Yeah, if you haven't picked up any old assignment, I have still a pile in my office. I bring it once to the class and then it remains in my office if you want to pick it up. I will update the marks for assignment 5 also. And 6 is with the TA, 7 is with you. And what else? So today I will give it to you maybe around 10 o'clock or so. So you'll have half an hour. You may be able to finish it. These are, if you know it, it's a short question. There is only one substantive part where I'm asking you to fix the errors in the program and then ask what the program does. So trying to understand what a MATLAB. So that's the only MATLAB type of question, not a single liner, but to understand how to solve a whole problem. So these in the exam also will be like that and will be taken from one of your earlier assignments or variations on that. So I know that when you have done the assignment, I think you guys are doing well in terms of scoring high. I want to make sure that you really understand that. So this is my way of reinforcing and checking how much of it you have retained from the assignment. Now, in the last, before I continue,
Real quick, there's an ChE meeting tonight. All the information is on the board. Quick show of hands. How many people plan on coming to now cases yet?
I'm like a 7%.
Got it. All right, thanks, guys.
well, you should get involved. It's your organization. You're going to be the one to carry this organization forward. So get involved. All right. Any questions about any aspect of this course?
I was trying to run the new pad to people like you just enter a new pad, right? Just didn't tell me the problem. I tried in 2 different problems.
In the library? Okay. So that the question was, why doesn't NewPad work on some of the computers? I'm glad at least some of you are kind of exploring this outside of the class. You need separate license for each toolbox in MATLAB. MATLAB has hundreds of toolboxes. And engineering faculty has a set of licenses that includes symbolic toolbox. So it should include MuPad. So meaning if you try it in engineering building, you might have a better success in using MuPad as well as in chemical engineering because we are living off the license from the faculty, College of Engineering. In library, they may not have it. I'm not sure. I have never gone to the library to check. It doesn't work. Yeah. Okay. So keep those feedback so that I can learn about. I'm new to LSU relatively, so I guess I've been here as long as you have, but I'm not exposed to as many parts of the campus as you are.
Do you need to pay separate money for new pad?
If you get a student license, then I think it's symbolic toolbox is included in that. Student license is about $100. You get a book and you get the software, and it comes with a set of toolboxes, not as extensive as College of Engineering license, but it has the basic ones like curve fitting, optimization toolbox, symbolic toolbox, and the basic MATLAB software. Simulates also. MATLAB is really like an ocean, and all we are doing is kind of exploring the shores of it. Okay? So, in the last lecture, towards the end of the last lecture, we saw how to use this CF tool in MATLAB. And I'm going to continue on that and then move back to do a little bit of theory of least squares curve fitting. We have seen a standard curve fitting, polynomial curve fitting. So what you should retain from this is the idea of when do you get a linear curve fitting model? When do you get a nonlinear curve fitting model? What makes it a nonlinear model and what makes it a linear model from the point of curve fitting? Okay, and what is least squares, and what is how do you assess the accuracy of a fit? And as I said, a lot of this you can do in MATLAB using the graphical user interface, GUI. So you really don't have to program it. And other feature that we saw, which is actually available in all stages of MATLAB, is you can develop a code. You can ask MATLAB to write the code based on what you have done on mouse clicks. Okay, and then it writes a function for you. That function can be used with other data set. So it really increases your productivity. And it goes, of course, much beyond that. You can take that function file and compile it into a DLL file and distribute it. So for those who are really involved in developing your own code based on MATLAB and distributing it to other parts of the company, there are tools available for that. But let's look at the problem of curve fitting from the steam table. Okay, so in the last lecture we saw 4 numbers over a range of about 16 degrees or so, and we saw that the data could be represented almost like a straight line. And we saw we could do straight line, which would be a least squares or quadratic or cubic. With 4 points, a cubic would be an exact fit at those data points. But there will be errors at other points. We won't know what the errors are because we don't have data. Okay? So CF tool does a lot of statistical analysis on the data to give you confidence intervals, for example, on the coefficients that it explores. So there are a lot of powerful algorithms that are built into CF tool. We saw, for example, F-min search in one of the assignments. What does F-min search do? Do you remember? Searches for minimization of a function. So if you give it a function, it finds out where the minimum is. How does it do it? How would you do it based on calculus? You'll take the function, take the derivative, set the derivative equal to 0, because at the minimum, you know the derivative must be 0. But MATLAB doesn't do that. It searches. Okay, so it simply changes the values of x and sees whether the function is decreasing or increasing. From that, it finds the minimum. And that is used, for example, in CF2, because it is converted into either a system of linear equations or an optimization problem. So in the case of a least squares, it is converted into an optimization problem. The theory behind that we are going to see today. In the case of regular curve fitting, where you have exactly 4 points and you want to fit a cubic, you convert that into a system of linear equations, which we saw in the last class. So in an exam, you should be able to set up that matrix. Okay, given a set of data, build that matrix. You don't have to invert it, but build that matrix. You should be able to go through the process for both regular fitting and the least squares curve fitting. Let's import the data first. So there's going to be a little bit of repetition of what we saw in the last lecture. So this is coming from Excel. MATLAB has import mechanism for a wide range of files. Okay, if you have just flat tables of data, you can import it. If it is in an Excel spreadsheet, you can import it. You can import images. You can import a photograph, for example, and then do image manipulation on that using the image processing toolbox. So this is what you get from the Excel spreadsheet. This is an import wizard. It's trying to get the data from the Excel spreadsheet into your workspace in MATLAB so that you can do processing with it. So I'm going to pick next, and it tells me these are the kinds of data, and I just want only the data from there. I don't want any text files. So I finish that, and it imports one data structure. Okay, and that data is 394 rows and 4 columns, and it's a double precision number. Okay, so when I click on that, it opens up the array editor and it shows me what the data are. Now this is not from Excel, but from MATLAB, the array editor in MATLAB. So I'm going to select that and create a variable, and it automatically creates that column extracting only that column, 39 by 1, and puts it into a variable called unnamed. I'm going to call it as TC. This is in degrees Celsius. Okay? And the next column is the saturation pressure. So I'm going to create a variable. It again creates it as unnamed. Okay? So I'm going to change that as PS, the saturation pressure. The next one is enthalpy of the liquid, HL. Okay, there. Okay, so I have extracted information. I'm just going to show the first two columns, how to fit the data. If there are any questions, if I'm going fast, please stop and ask me to repeat it. Okay. So in the workspace now, I have a variable called TC, which has all the temperatures in degrees Celsius from 0 to 374 degrees for temperature. I want to convert that into Kelvin. T is equal to T plus 273. TC. Thank you. I'll call this as TK, degree Kelvin. Okay. So I have another variable called TK, which has the degrees Kelvin. P is in PSI, and I'm going to live with the PSI units. So what I want to do is develop a functional relationship between these two, express it in the form of a curve-fitted equation. Why would I want to do that? I could, for example, store this entire data in HYSYS, because I would need this data in HYSYS when I'm doing the calculations. As we saw, it needs K values, it gets them from a model, from an equation. When it needs steam properties, we are doing a boiler design, you need this data. Okay? So you can either store them as data, in which case you'll be storing massive amount of data because you need to save all this data for every chemical. There are probably 3,000 chemicals in the database. Okay? Or you can capture them in the form of an equation, then all you need to do is save 3 or 4 coefficients. You can regenerate it at any point that you want. So the interpolation problem is also solved for you. So that is the reason why we build these models. And in your own course, when you're doing the lab, for example, you'll be getting data and you'll have the need to fit the data to an equation. This would be an excellent tool for that. Okay. So I'm going to start this. Another thing I think a few people have asked me, how do I know what functions are available in MATLAB? And here is this function icon. So if it's a function browser. If you click on that, it tells you what are all the functions that are available, what are all the toolboxes that are available. Okay. And here is a curve fitting toolbox. And it says fitting curves and surfaces. So there are tools here that can fit two-dimensional data. What do I mean by two-dimensional data? Data that depends on two independent variables. Okay. Then you can put a surface as well to that and fit it. So here, data fitting, CF2. And whenever you place the cursor on that, it gives you automatically the help on the right-hand side related to that. You can learn more about it. Okay. So it's really very nicely done. So once you select that, double-click on that, it enters that function name CF2 for you and places the cursor there, and you hit enter. You have accepted to run that command. Okay. So then it opens up this graphical user interface for curve fitting tool, and we need to first import the data. The meaning is it's already in the workspace, but you need to import it into the toolbox. So the X data is going to be in degrees Kelvin, and the Y data is going to be the saturation pressure, and I create the data. So it automatically gives it a name, PS versus PK, and you can smooth it if you want. Now, what does smoothing mean? What do you think? You have to guess. Pardon me? Making the curve is what we are going to do at the end of this exercise, but before we go there, we are saying that we want to smooth the data. So if the data is noisy, okay, that meaning that when you plot, it's not going to make real noise. Noisy means. Okay, so I'm plotting PS versus TK. Okay, in this case, the data is actually smooth. Okay, so meaning I can put a smooth curve. Visually, I can see. Okay, but if the data looks like this, that would happen when you are getting experimental data. Okay, so this is what you would call a noise. That is, the data has a mean trend, but there are random events in there that causes the temperature to fluctuate around the mean, for example. So when you have data like this, that is on a band but scattered, then you would want to smooth it. Smoothing basically means it tries to filter out, it tries to remove the noise and gives you a smooth data. So there are many algorithms for doing that, and the CF tool gives you the option to smooth. But in this case, I don't need to smooth the data, so I'm just going to accept the data as it is. Okay? And so I close that. So I have, sorry.
Is it going to take out outliers?
Okay, that's good. So you remember something about statistics, right? What is an outlier?
It doesn't the trend of all this.
Exactly. So if it gives you exclusion, okay, so you can exclude a certain set of data using certain rules. So an outlier, this is a very important concept, which you might have seen in a statistics course. An outlier would be a set of data points somewhere here. Okay, and then the trend continues like this. So what happens is your recorder probably went berserk, got some external cold wind blowing it up. Something happens in the plant that shifts the data outside. So by visual inspection, you see the trend. Okay, that doesn't fit. So these would be called outliers. Okay, then you can exclude them. Because if you include them and try to fit it, your fit will be very bad. Okay, so you should know what outliers are, and there are mechanisms for eliminating them. But the smoothing process is removing these fluctuations. If I plot this by line, it's going to look like this, passing through every point I have. Okay, and that is what we would call a noisy data. And what I really want is a smooth line through that. Now, least squares is in fact one way of filtering or smoothing. But before you go there, this algorithm allows you to just filter the noise. Any other questions or comments? Okay, so the data that I took from the website offers this in two ranges. Where do I have that? I guess I didn't copy that. Okay. Pardon me? I have the link in the bottom. Yes, I do. But I don't know whether the link is going to work because my internet is not working. So some of you have seen the link. The link is there. You can go there and you can look at the form of the expression that they suggest would be best. But I don't know about that, so what I'm going to do is try a simple fitting options. Okay, so first thing I'm going to try is select a new fit and fit a cubic polynomial and apply for the whole range. Okay, so it gives you the fitted curve and it gives you the coefficient of the polynomial. Because I picked a cubic, it has 4, and there are some data that you should be able to interpret. P1, P2, P3, P4 are the unknowns or the coefficients, what we call A1, A2, A3, A4. Okay, it gives you what is the best value for that, and it gives you the range. Okay, so that is called the confidence interval. That is, it does some statistical analysis on what is the best estimate of those parameters and what is the 95% confidence interval for that. So the data, those coefficients could be in this range with a confidence of 95% in the data. Okay, so if the data is more scattered, there is more noise, you will see these numbers much more spread out. Okay, so if they are very narrow, that means you have very good confidence in the data and the data is fairly smooth. Now, this is not a good fit because it gives you negative pressures. The data that we have, that we imported, if you look at the pressures, it doesn't have any negative value. It starts at 0.6 and keeps on monotonically increasing. So that's not a very good fit. So what they did in the Wikipedia link is to take the first 7 data points and fit a separate curve for that. And then the next set of data points, a separate curve for that with the same functional form. And that's what we're going to do. Okay. So I'm going to create a lower range, TL, and extract in that 1 to 7. So what I'm doing is I'm taking data points from 273 to 333 degrees Kelvin, 7 data points, and I need to extract the corresponding pressure, PS 1 to 7. Okay, so I have created 2 new data points, okay? TL and PL. These are for a subset of the data over which I want to improve my accuracy, okay? And of course, in CF tool, if you look at other piece of data, goodness of fit, the one number to look for is this one, root mean square error, 188.8. What that means is the difference between what you predict and the actual data that is taken from the table, when you average them out over all the data points, that is a fairly large number, 188. Okay, so you want to bring that down to an acceptable level. So one way of doing that is to break it up into smaller sections of the data. And so let's create another fit 2, and I'm going to this time again I will try a cubic polynomial. Okay, but I want to use a different set of data. Okay, so I need to go to the data and pick the data TL and PL. What did I do? Did I save it or not? Create data set. Okay, so that saves a second data set with only about 7 data points, going from 273 to 333. Now, once I have created the data set and labeled it, it becomes available for me here. Okay, so I can take a smaller subset and go through the same process now. So this is fit 2. And it tells you at the bottom the summary. Fit 2 is between PL and TL, a lower range, and it's a polynomial of degree 3. And its root mean square is much, much smaller, 0.1273. Question? Okay, so that's how you manage to control the goodness of the fit. But what observation can you make if I give you that graph? I have 2 fits there.
What's your pressure changing faster as you go higher?
The cubic fit that we obtain using a lower range is an excellent fit only in that range. If you go outside of that range, for example, to 500 or 600, that's a cubic fit, the second fit, okay, using a smaller subset of data points. That becomes a very poor representation of the data. So you'll be extrapolating that, and you never do that because you can see what happens here. Okay, but the other fit using the entire data points does a good job overall, but the error even at the lower point would be much higher than the one that you obtain using the lower degree. Now this is the CFIT tool has a number of such fittings for you that are available. But as I said, never go for a very high degree polynomial curve fit. Why? Because it has these fluctuations. Did you have a question?
Is it possible to truncate the curves once per day?
Right. You can certainly, when you are calculating, when you are evaluating this, you should truncate it to the range. But when you are displaying it, it has a tool. I'm just learning these things as I go along. So here is the axis limit control. So immediately it puts the limit. So here I can say, set the limit to 340. Okay. So I'm fixing the range, X range from 269 to 340. The curve looks really strange, but what I need to do is limit the Y range too. Maybe let me try 400. Okay, let me just check the range of data. PL goes from 333, PL to 19. So let's fix the range to that limit. Okay. So I want this to be 19 or 20 upper limit, and lower limit is 0. Okay. And that was a good suggestion because I never went through this. So now you're zooming in on the range over which you have fitted the data for the second fit using the smaller subset of data, PL and TL. And you can see the blue curve is an excellent fit in that range. You can actually move that. But the red curve that we did originally is really a very bad fit in that range. Okay. So one way of getting control over your curve fitting is do subsets of data, okay, and use a low degree polynomial, a cubic polynomial. You will get much better indication, and you should know how to read that. The way that you read that is by looking at the R square and then the RM SE, the root mean square error.
Is there an exponential model that you can use?
That's what we started doing in the last class towards the end, because the website suggests that a polynomial is not a good fit, but a power law expression derived from Antoine type of equation. So there is a thermodynamic reasoning for going for that functional form. You will see that in a thermodynamic course. And so there are, that could be a nonlinear curve fit. Now this is a polynomial curve fit, is a linear curve fit. Okay. Where does it say? Fitting options. Least squares method. It uses least squares method. And let's go for Gaussian custom equations. Okay, so I can create my own custom equations which are suggested to me by other theory, like in thermodynamics, vapor pressure versus temperature data is given by the following expression. Okay, so it is now remember x and y are local variables within the function, so I don't have to call them t and ps. This is an expression for the functional fit that I'm doing. So I'm going to call x as my independent variable, which will be the same as pressure, saturation pressure, the temperature, and y as my saturation pressure. Okay, and I'm going to pick the general equation, and I'm going to replace that with 10 to the power a minus b divided by x minus c. This is the functional form suggested by thermodynamics as the best functional form for curve fitting saturation temperature versus pressure data. Is this a linear or a nonlinear model? To answer that question, you need to look for what is it that I'm solving for, or what is it that is known. In curve fitting problems, x and y are known. They are the data set. A, B, C that appear in this equation, or P1, P2, P3, P4 that appears in the polynomial equation, are the unknowns. Okay, so for polynomial curve fit, that unknown coefficients appear in a linear form. So that is called a linear curve fit. Whereas here, A, B, and C appear in a nonlinear form because you have 1 over x minus c, for example. Okay, so this would be considered as a nonlinear curve fit. So this is a functional form, and I can put a starting point, because what it does at this stage is MATLAB will call fmin search. Okay, and it will try to search for A, B, and C, the best values of A, B, and C, that minimizes the error between what it predicts from this equation and what the data point is. And we will see the theory behind it pretty soon. Okay, so I need to give an initial guess. By now you are familiar with these ideas, right? When you're doing an iterative improvement, you need to provide an initial guess. So I'm going to give an initial guess of 1500, 30, something like this. Okay, that's only an initial guess. And then I say, okay, go ahead and apply the fit. It's computing the best fit using that data set PL versus TL. And what is the root mean square error now? 0.08. Okay. Did you have a question?
How did you know?
How did you know?
How did you know A, B, and C that's 3 unknowns?
Okay, the form of the equation is known from Antoine type of equation in thermodynamics. The actual values of A, B, and C, you really have no idea when you start that. Okay, so you just have to put some numbers. There is a problem that you might encounter. That would be when you're forming this objective function, the objective function could have, what is the objective function? The objective function is nothing but the error versus A, B, and C in a third axis. So it's a 4-dimensional figure that you need to imagine. So the error is going to be a surface, something like this. And the surface can have several minima or maxima. So what the fmin search does is tries to find that value of A, B, and C that minimizes the error. So you could have a local minima with a different set of parameters, but that will have a larger error than a global minima. Okay, so you need to try different initial guesses when you're doing the search to see which one gives you the lowest error. That could be that would happen if you have several local minima in the problem. Okay, so the fit 2 is what is that? Fit 2 now is this nonlinear fit using the Antoine equation, okay, with an error of 0.08327, and that fit is the blue line that you see here, which is very good. The cubic fit also does a very good job over this range. But what I wanted to drive is the difference between a linear and a nonlinear curve fitting. I'm not going to include this in the midterm now, but in the final. Okay, so you should be able to, if I give you a set of equations and say I'm going to do a curve fitting, is it going to be linear or nonlinear? You should at least be able to tell by looking at the problem what type of fitting that we are doing. Okay, and of course you can do analysis. Analysis simply means using the fit, evaluate at a set of data points. So it will give you fit 2, line. Oh, evaluate. So it gives you, if these are the temperatures at which you want to evaluate the vapor pressure, it uses that equation with the fitted parameters to predict the values. These are the values. Okay, and you can plot that also on the same graph to see how it does. But the nice thing about CF tool is it also allows you to calculate the first derivative from the fitted data, or the second derivative, or the integral. We will see the theory behind it later on in the next 3 or 4 lectures. Okay, so that's in a nutshell what curve fitting is about. Okay, with the CF tool, it's a very powerful tool, as powerful as this. When you leave this course, if you know how to use and understand a set of about 5 or 6 tools, you will be able to solve most of the mathematical modeling problems in process engineering. Those are F-min search, F-solve, ODE 4.5, BVP 4C, and you'll see a few more for integration and differentiation. And they have behind them a very powerful set of algorithms, so you should have some understanding of how to use them, how to interpret the results, what are the errors, what are the tolerances, what is the rate of convergence. These are ideas that you should be able to appreciate and express. Any questions? Okay, I still have about 15 minutes. I don't know if 15 minutes is enough, but let me just talk about this idea of least squares minimization. What is the difference between regular curve fit and least squares minimization? And then we will move on to the quiz. Okay, the idea is just a simple extension of what we have seen so far. Okay, so what we have seen so far is you give me a set of data points, f, the function, and x, at which the function is given. Okay, so those data points I can plot y against x. And what I want is to fit a particular equation to that. And that equation earlier we saw was the polynomial, but it could be anything. I could plug in Antoine equation in that location that I have circled here. Okay, and that function will have certain number of unknowns, a, b, c in the case of Antoine equation, or p1, p2, p3, p4, a1, a2, a3, a4 in the case of polynomials. Okay? So here I'm just using the polynomial again. Okay, my task is to find the best values of these coefficients a1, a2, a3 in such a way that the error is minimized in some sense. Now, if you give me exactly enough number of points, 4 points, and the cubic, I can make the error equal to 0 at those 4 points. That's what we did in regular curve fitting. That gave us a system of linear equations. Now, this is a linear curve fit because A appears by itself. There is no A square. There's no 1 over A. Okay? It's a linear problem. Just because x to the power 3 or 4 appears, it doesn't make it nonlinear, because those are known numbers we can calculate. Okay? The main difference is now I have more data points, and that's the key. Okay, more data points than the polynomial I want to fit. So the polynomial degree is n. Fixed ideas. I want to fit a cubic polynomial. I have 4 degrees of freedom, 4 unknowns, but I have 2,000 data points to represent that equation. Okay, so m is a very large number. Okay, n is much smaller than m. The degree of polynomial is much smaller than the number of data points that I have. That's when you would use the least squares fit. Automatically MATLAB does that. polyfit automatically switches to least squares if the number of data points is more than the degree of polynomial you have chosen. But if they match, it will use a regular fitting. So what we're going to do is we're going to define an objective function. J is called the objective function, which is what fmin search needs. Fmin search should be able to calculate that objective function for a given set of parameters. So A here is a vector of unknowns. So I give a set of A, then I should be able to calculate that error. Can I calculate that error? Obviously I can, because if I give a set of initial guesses for A1, A2, A3, A4, then I have a tentative values for those. I know xk and I know fk. So this entire error can be calculated at every point. And I square the error, sum it up over all the data points, k going from 1 to m, and divide by m. So the error per data point. That is my objective function. So what I want to do is I want to minimize that objective function. How do I do that? Calculus, right? If you have a function and if you want to minimize that, take the derivative of that function with respect to the unknown, set it equal to 0. Because at the minima, you know the derivative is 0. But you have to do that for each one of the A values in that expression. So if you have 4 values of A, A1, A2, A3, A4, take the derivative of J with respect to A1, J with respect to A2, with respect to A3, with respect to A4. Each one will give you one equation. The moment I go into theories, I see, why do I need to do that? I need to know how to do it, not why. You should know why also. Okay? You should know why also. All right. So there is a lot of equations here. I need to take more time to explain this. So maybe at this point, I will leave it, come back, and go through this derivation to implant in your mind the idea of minimization, least squares minimization. Okay? So we will stop there and get on with the quiz.